Kia ora, everybody. I'm Emmeline Pat Dahlstrom, and this is Eric. And we're from Space Base. So really sorry that we're not able to be in Wellington today because of the lockdown, but also it gave an opportunity for others who are in different regions to actually join us this afternoon or this evening. So that's actually great. So in terms of the agenda for today, for the 1 hour, we're actually doing a briefing for the Space Challenge, so all about the project, the problem areas, the tech, the tools, and then also we have a special guest as well, talking at the end of the briefing. So maybe just to kind of start the ball rolling, I will share screen. Let me go here, right. So yeah, just to start the session here is like, I want to kind of like point out why we're sort of like doing the challenge. And, today we're all, the whole world is kind of like focused on COVID and the pandemic, but really climate change and its impact is still really on the rise and is really felt kind of like all around the world. As you can imagine, all of the increase in natural disasters with record temperatures and drought and like super typhoons that are happening this year is all attributed to this. And actually the latest like IPCC report validates what we already know, which is that climate change and global warming is human induced. So really the biggest challenge for us today is to reduce greenhouse gases, and New Zealand is fully committed to carbon zero by 2050, but we're also running out of time. So I guess for Space-Based, we really think that researchers and the academic community, specifically students, can play a much bigger role for accelerating the CO2 reductions through research and also through innovation. So the good news here, though, is that also the technology has been exponentially developing, and so therefore, with technology, we have smaller, cheaper, faster. And it has democratized the access to space technologies today, which is like not the same as like 10 years ago. So today you can actually make a difference with the information that we have today. Data is free, especially for researchers and academia coming from government-owned satellites. Although in this particular challenge, we are also going to leverage some commercial satellite data as well. And then also in the past, these analytical tools are also very expensive. But today you've got platforms like QGIS that are open source that can be leveraged. And so for anybody, really, you only need a Wi-Fi and a personal computer to actually be part of this potential movement of helping us with reducing climate change. And what we really want is actionable information. So not just monitoring, but really something that we can actually leverage to reduce carbon and reduce it. So our ask for you today really is to invite you to create teams and to define an approach, and we'll talk about the problem areas, and then apply to join the incubation research program that we will be delivering around November to January timeframe. So I'm going to turn you over to Eric to talk more about the motivations of the actual problem areas that we're dealing with.
Hi, yes. So I wanted to give a little bit of background and reminders about the climate change and the motivation for the problem areas we were picking. And then I'll get into more of the two problem areas that are in this challenge, which are carbon sequestration and coral health. And then Emmeline will go on and talk about the details of the process of applying this. So back to the basics of climate change. This is a overview chart showing the that has the energy balance across a spectrum here, with the solar energy coming down in the visible light mainly, and then over here in the infrared is where the heat from the Earth is re-radiated back into space. And so you have to have this energy balance. And the problem that that's been going on is that we've been increasing the level of CO2 and these other greenhouse gases, which are blocking more of the infrared radiation from back from the Earth, and the Earth heats up until there's an equal amount of energy going back out into space. So the temperature is actually rising in order to get this energy balance. Let's see. Okay, here we are. So basically, after tens of thousands of studies and analysis and lots of satellite observations, the basic conclusion from this latest IPCC report is that there's overall across the Earth, there's a increase of 2.72 watts for every square meter. That's more energy coming in from that's being trapped in the Earth system because of these greenhouse gases. And just about 3 watts per square meter doesn't seem like a lot, but if you spread it out over the entire surface of the Earth, it adds up to a huge amount of energy. If you measure that in atomic explosive power units it's equal to 330 kilotons of explosive power per second. So it's basically like 20 Hiroshima bombs going off each second as the amount of energy that's being added into the Earth's environment. And that's where you get all the warming of the oceans and the land and the atmosphere and the cyclones and driving the weather systems and things like that. All this extra energy is going there. So then the problem is caused just by this steadily increasing levels of greenhouse gases, mainly carbon dioxide. So we have these projections in the latest IPCC report of all these different scenarios in the future, like if you continue on business as usual, or you end up with huge amounts of carbon dioxide and huge warming of the planet. And so the Paris Agreement and all these other agreements are trying to bend the curve and reduce the carbon dioxide emissions. And then the last ones that are really aiming for maintaining the temperature of the Earth to not increase that much, they depend on a lot of carbon sequestration, a lot of removing the carbon dioxide from the atmosphere and storing it in biomass, et cetera. And so that's a motivation for where our problem statement is, which is looking at the how you capture more carbon out of the atmosphere, remove from the atmosphere, and store it in biomass. This is from rough numbers of the, there's that 40 billion tons, 40 gigatons, which are billions of tons of carbon dioxide emitted each year, and its overall sinks removed from the atmosphere or about half of that. And each country is trying to assess how much is being emitted by the countries and how much is being absorbed. And New Zealand has made a big effort to try to document how much carbon dioxide it thinks it's being removed by the plants in New Zealand. Australia is very uncertain. It's 20 million tons removed by in the coastal areas, and there's a potential for hundreds of millions of tons to be removed on land, but it's very uncertain. And also the Pacific Islands is very uncertain. And so in the future, these numbers are going to be very important for reaching these targets, and also potentially very valuable on an international trading scheme. So in the different types of carbon sequestration, you have, let's see, we have these land and coastal zones from forest and native bush and pasture and wetlands And then you have what's called blue carbon in the mangroves, salt marshes, and seagrass. And then there's the open ocean. And so a lot of these numbers are very uncertain, and especially on the pasture number is very highly uncertain. And so that's part of the target of this challenge is to try to understand better what these values are and be able to document them from using satellite data. Because right now, for example, New Zealand has this scheme for emissions trading scheme where it gives credits for growing forests, and there's sometimes you can get credits for native bush, and the going rate is about $36 per ton of CO2 captured. And so, but it's something where it works for standardized, exotic forests, but doesn't work necessarily for all these other areas that are have a potential benefit. And you can really, if you can give an incentive to landowners for preserving wetlands or pastures and things like that, that would be a big improvement over the current situation. So in New Zealand, there's the standardized report approach is to require a lot of on-site verification and measurement of trees, physically going out into specific locations. There's other companies that are starting to apply satellite remote sensing to identify credits for blocks of forest, and then so there's, but it's still trying to fit within the current system, and if what we think there's opportunities for generalizing these for other land types or marine areas. So this comes down to our problem statement, which is using satellite data in combination with other data sources help develop verifiable methods to improve or to measure carbon sequestration on land or in coastal areas. And so the idea is that you want to come up with an approach that would address at least some part of this and advance the areas in, for example, in these different land and coastal areas, or and you have not only the planet data from our partnership, but you also have all these other free data sources that are provided by the US government or the European government. And just to give you an illustration of some of these different data sources, New Zealand currently in their land use maps applies, Sentinel-2 multispectral data to categorize different kinds of land cover, and they also do ground truth on specific sites and collect that data for these reports across the country. With what we're offering in this challenge also is access to planet images, which are daily revisits of in the visible light and near infrared, and with about 5 meter resolution. And then, but we're also suggesting that you may find useful information in other bands in the multispectral data in Sentinel or Landsat to give you better ideas about what kinds of plants or native bush or things like that. And then there are other possible approaches of using LiDAR lasers with either airborne or ISAT-2. And then there's microwaves that detect properties of just in the subsurface or the different aspects of the radar data that can penetrate a little bit farther, because there's a lot of carbon that's being sequestered in the root systems also. And so for this challenge and this partnership, we have access to the Planet platform with a specific research license and 5,000 square kilometers per month of data from their current PlanetScope and Rapid Eye archives, and also training and support. And this is just an example of some of the planet data being used right now for this company in New Zealand that monitors forests. That, for example, they're able to see that this area has winds knocked down some of the trees just because Planet monitors every day, and then this is a higher example of the higher resolution version. So that was all the carbon sequestration problem. Now the other problem that we're included in this challenge is the coral health. Help improve the monitoring of coral health changes due to climate change using satellite technology. And for this, this is the main resource is this Allen Coral Atlas, which uses planet data, but has been analyzed and maps different categories of coral and geomorphic information. And so you have a big issue is trying to identify live coral and dead coral, because the dead coral can be threatened both by warming oceans and also oceans acidification due to climate, to the carbon dioxide, and then also coral can be under stress from a number of other areas, overfishing or from pollution, or even runoff from the rivers. And so the coral data, the Allen Coral Atlas, we have a video coming up that gives an overview, but it's really an extensive database of the status of corals with at least 3 layers of different years. And it's possible also to apply some of the new planet data to the same issue. One of the peculiar challenge for coral is that healthy coral actually has these animal microorganisms that have algae trapped in a symbiotic way inside the coral, and then when it's killed by one of these by heating or acidification event, it can be bleached, and the algae gets out of the dead coral, and then turning around, the algae grows on top of the dead coral. And so the Allen Coral Atlas has a real challenge with distinguishing between healthy coral over here and dead coral that with algae on top. And so they would be very interested if anybody can figure out, different wavelengths or whatever to try to identify, help them clarify between the healthy coral and dead coral with algae. And so this is an example of the Allen Coral Atlas platform. And this next video summarizes the Allen Coral Atlas.
Yeah, this is the video that was used during the opening of the challenge, and it actually is really a great summary. So we're just gonna run this.
Thank you so much for joining us. I'm overjoyed to share the Allen Coral Atlas, a new tool for coral conservation. Thanks, Emmeline and Spacebase, for organizing the Space for the Planet Challenge. What a great way to ignite some new ideas. First, I'd like to highlight this has been a true team effort. This co-author list is just a subset of those working on the Atlas. I'm Brianna Bambick, a coral reef biologist by training and virtual reality producer as a National Geographic explorer. Now I lead the field engagement team. And I'd first like to invite you to all explore allencoralatlas.org. To set the stage, our team has a few goals for today. We want to share the Allen Coral Atlas mapping and monitoring tools so you have a basic understanding if you want to use them in your project. We also hope to connect with the space-based community so you all have access to not only the Atlas platform, but also the training courses and resources we have freely available. And of course, we encourage all follow-ups and questions. The Atlas team started with 2 major challenges. As Charles Darwin discovered, mapping reefs is not as straightforward as observing and mapping land. And as coral reefs are one of the most biodiverse and threatened ecosystems on the planet, How are they still largely unmapped and unmonitored? And how are we supposed to protect what we don't know? So the Atlas is overcoming these challenges twofold by creating the world's first globally consistent map and dynamic monitoring system of the world's shallow coral reefs. It started with Planet Inc. and Andrew Zoli's fleet of over 150 Dove satellites, pictured here. The central portion is about the size of a loaf of bread. These satellites can remotely sense the planet with high-resolution imagery. Then, Arizona State University's unique ability to essentially remove the seawater corrects for cloud, sun, and wave reflectance. We will use this satellite image of Heron Reef, Australia as an example. In the top left corner, you can make out the actual island and the surrounding reef. Here you can see an incredible level of detail. First the image, next the map. Here, University of Queensland's Remote Sensing Research Center uses field data collected by survey teams and existing data sets to generate the maps with object-based analysis and machine learning techniques. Each color represents a different benthic class. For example, microalgal maps, sand, and the coral algal combined layer, down to a depth of 10 meters. The Atlas also provides the first ever globally consistent geomorphic map layer, condensing dozens of reef categories into 12 globally consistent geomorphic classes, down to 15 meters. Next, the Atlas also includes a quarterly turbidity monitoring system by Arizona State University. This is a sample turbidity image, since it is for download only and shows the highest level of turbidity per pixel for the quarter at 10-meter resolution. Curious minds could look into how land and sea interact around the world using this turbidity monitoring system. To show you the newest Atlas feature, which detects global coral bleaching, let's travel to a beautiful island in Indonesia. This archipelago was monitored July 5th of this year. As surface temperatures became warm, NOAA's Global Coral Reef Watch sends bleaching alerts, as shown in yellow. So when a region signals a bleaching alert, the Atlas bleaching detection tool is initiated. Here, we are going to zoom into the north of the archipelago. You are able to see different bleaching severities across the islands, shown by low bleaching in yellow, moderate in orange, and severe in red. We are curious how you might use the Allen Coral Atlas bleaching detection tool. We hope these new marine technology tools spark some curiosity. And here are a couple more suggestions I have from working with researchers and conservationists worldwide. One need is identifying biodiverse areas that have multiple stressors to identify priority for conservation. Another potential use is identifying erosion and monitoring the surrounding area. How can you scale this up? Or how can you find patterns in coral health and connectivity? What IUCN red list species do we want to include in this monitoring effort? And how do we inform policy? Do we want to identify best practices by countries, potentially approaching marine spatial planning and conservation priorities? Up to you. This is a short introduction, and we have plenty of resources on the Atlas website and the YouTube channel, including this online course to keep your wheels spinning on how to use remote sensing and mapping for coral conservation. Here's a list of links for the online course resource. And we, of course, encourage all types of communication, especially in the virtual world. You can sign up for the newsletter to hear about new features, try out some of the tools and the data downloads. Please let us know how we can be of assistance. Reach us at these emails. And lastly, good luck everyone with the Space for Planet Earth Challenge. We would love to hear about your project or proposal that might integrate the Atlas. Please let us know so we can highlight your work. See you out there.
Yeah, I just wanted to note that the video is actually on the website. So I know that there's a lot of links on that video and lots of resources. So make sure to check it out on the video. So the next part of the briefing is I just wanted to go and talk about the mechanics of actually participating in the challenge. Again, as Eric mentioned, there are two categories to the challenge. One is for high school and one is for university. And the high school is going to focus on the coral health, while university is going to focus on carbon sequestration. The application requirements, very simple. It's either you're a high school or a university student, or if you're a startup. And for simplicity's sake, we actually define startup as like either a group or a company that has like less than or no more than 20 employees. And then that you actually reside in New Zealand, Australia, and the Pacific Islands. In terms of the prices, so there's a cash prize for the university startup for 30,000 New Zealand dollars, and then for the high school category, it's 10,000. And then also an equivalent of 15,000 in data vouchers from Planet, as well as mentorship from Spacebase for 6 months. And for the high school, there's also a scholarship for the team, up to 6 members, to participate in the US-based Mars Moon Virtual Astronautics Academy program. So essentially what's going to happen as part of the challenge is that we're running a virtual research incubator between November to January of 2022. And the virtual incubator would basically include like webinar sessions from design thinking to prototyping, and then access to specific satellite data from our partner Planet, and then also mentorship. To be able to participate in the incubator, you basically need to submit a short proposal of your idea, which is about 2 to 10 pages before before the 31st of October 2021. And basically the proposal has like several elements, of which you have to basically list who the team members are, what specific area of the problem area you are going to be addressing, your technical approach, also an outline of your plan and your schedule, and then if you have any other specific, also ask for support. In terms of the judging criteria, we're using the judging criteria for all of the stages of the challenge with this rubric. So really the use of the space technology, and then technical feasibility. So is it science-based? What's the innovative solution? Is it a new or a novel idea? How are you implementing it? And then also we're also looking for maximum environmental impact, as well as what state your prototype is going to be at the end. And then there's also additional points if you show that there's going to be some evidence of impact on the short term, and then if you're collaborating with other stakeholders, as well as using other technologies, as well as team composition. So the final selection process, the final deadline for the application is really the 31st of January. And just to note that you can actually submit an application even though you don't get selected into the incubator program, or you don't participate in the incubator program. And the requirements really is just like a 5-minute video demonstration of what you've done, and then also a presentation deck of what you're going to be pitching. At the end of the 31st of January, we're going to be down selecting to 3 finalists from the high school level, and then 3 finalists from the university, which will then, we would invite to participate in a demo and pitch session on the 18th of February here in Christchurch. So going back full circle from what I mentioned in the beginning, we're really looking for actionable outcomes from the challenge, which could be either contributing to already existing climate research initiatives in other kind of like institutions within the region, but also to incentivize really carbon capture using biomass for either farmers or organizations or individuals, and then that might be able to create new carbon credit schemes for government and decision makers. It could also, specifically for the coral problem area, it could create area of reserves, new reserves for endangered regions, and then also incentivizing citizen science for more ground truthing, and also more programs for sustainability in the region.
And I just wanted to mention that, the climate change problem can be overwhelming, but I think this is an opportunity where we think that people that attack this challenge may have a chance to really influence things on a global scale. And so it's a very unique opportunity with the satellite data and the tools that are available now, that you could really make a big difference that's what we're looking for, those people that will take this on and make a big difference in this global problem.